Good morning, everyone. I'm Jin Yang, a PhD student in the Department of Electrical and Computer Engineering of Duke University. Today, I will discuss about defending against machine learning-based inference attacks using advanced examples. This is a joint work with my advisor, Niao Zhenqiang. In machine learning-based inference attacks, the input is used public data, and the output is used private data. Basically, the attacker can collect some public data as well as private data from users who disclose their private data to train a machine learning classifier. Then the attacker can use the machine learning classifier to infer the private data for the user who not disclose their private data. So the machine learning-based inference attacker can successfully infer users' private data from their public data because these two are statistically correlated. There are many examples. Basically, the machine learning-based inference attacks are pervasive. For example, in attribute inference attacks, the public data could be the rating scores, page likes, social friends, and the private data can be the age, gender, and political view. In author identification attacks, the public data can be the text document program, and the private data can be author identity. In website fingerprinting attack, the public data can be the network traffic, and the private data can be websites. In membership inference attacks, the public data can be the confidence scores, gradients, and the private data can be member and non-member. There are also many other inference attacks, like the side channel attack, location inference attacks. Here is a threat model. Basically, we have three parties: user, defender, and attacker. The user aims to publish some data while preventing the inference of its private data. The defender can be a client in user side. The goal of the defender is to add some noise to user true public data before release it to defend against the inference attack. After observing the noisy public data, the attack can infer the private data of the user. However, there are some challenges. First, the defender doesn't know the classifier used by the attacker. To solve the challenge, the defender itself can learn a classifier. This relies on the transferability. Basically, the default classifier is very likely to have similar classification boundary. The second is that the defender needs to satisfy some utility constraints. So to solve the challenge, the defender can find a mechanism M star to add random noise. Here M star Rx is a condition probability that the defender will add noise R to use the true public data X. Then the defender can sample from M star to add noise. However, there are still some challenges to find the mechanism F star, because the probabilistic mapping from user true public data X to user noisy public data X plus R is exponential to the dimensionality of X. However, in practice, the X often has high dimension. To solve the challenge, we can categorize the noise space into M groups based on the output of the defender's classifier, C. So based on this, we propose a two-phase framework. In phase one, recall that we divide it into different groups. So for each noise group, we can find a minimum noise as representative noise. This can be said as an evasion attack to the classifier. Basically, here we find some adverse examples. Then in phase two, we can simplify the mechanism M star to be a probability distribution over M representative noise. Then we can solve the optimization problem to find the noise addition mechanism M star. So thanks for your listening. If you are interested with more details, you can read our paper. One is MemberGuard. It's defending against the black box membership inference attacks using adverse examples. And another one is AtGuard. It's defending against the attribute inference attacks by advanced machine learning. Again, thanks.